All right, in this segment, we'll come to a little the physical consequences of molecular shape. You might be asking yourself, like, why does molecular shape actually matter, right? I mean, if we know just the chemical formula and we know which atoms are bonded to which, then, isn't that enough to describe most of the chemical properties? But it turns out there's a lot of chemical properties where the shape of the molecule is important. So what we'll be talking about now is to understand how molecular geometry can lead to either polar or non-polar molecules. Why is that important? A polar molecule, it has a partial charge on one end and a partial negative charge on the other, and those can attract each other. Whereas a non-polar molecule can't really do that. So you get significantly different chemical properties in terms of things like boiling points and melting points, depending on whether it's polar or not. And that is directly related to how the atoms of the molecule are arranged in space. So let's look at some examples. Yeah, so a dipole, remember we talked about electronegativity and we talked about dipole bonds, that if you have a more electronegative atom, it's going to pull the electrons away and you'll get a partial negative charge there. And so when you have multiple of these molecules wandering around in space, then you get more attractions. Things like the van der Waals model of ideal gases don't work as well because that assumes that they have relatively weak attractions. But you can have relatively strong attractions with dipole molecules. And so they behave at liquids or solids at much lower temperatures. So for example, hydrochloric acid, we have a slight positive charge on the hydrogen and a slight negative charge on the chlorine. But even if a molecule is more complex, we can still have dipoles as well. For example, take a look at this. In this case, we have ammonia. And so for ammonia, you see that we have three sort of dipoles added together. We've got hydrogen bonded to the nitrogen. Again, the nitrogen is more electronegative, so it has a bit more of a negative charge, but that's the same for all three of them. Now, it turns out that if you look straight down in this and do vector algebra, you can see that in this direction, if you imagine that this nitrogen is sticking up in the z direction. In the x and y direction, there's no dipole. There's no net electric charge imbalance in any direction in the plane, but there is a clear electron imbalance up and down because the negative nitrogen weighs down there. So ammonia is also a polar molecule as well. Whereas something that's, for example, trigonal planar, if they're all the same molecule, will not have any real dipole. Formal charges, you can also look, if you're interested, you can also look at the formal charges. That usually gives a hint at where the electron density is as well as electronegativities. So, how about carbon tetrachloride? So carbon tetrachloride, if you actually go and do all the vector addition and you actually project vectors out in 3 dimensions, you can see that although there's a bunch of polar bonds, a carbon and chlorine have a moderate electronegativity difference, the vectors all add up to 0. So there's actually no net dipole in here. There's sort of a radial dipole. There's more electrons out at the edge and less in the middle, but there's no directionality to that. There's nowhere to if there's 2 of them together, there's no direction for them to attract. So there's no dipole there. And again, you have to go through and do the vector algebra in 3D, do trig to figure out, how much of a contribution to each of the bond there is. But when you go through, you find that, again, in this plane, that the 3 molecules that are, spaced at 120 degrees when you project them out into the plane cancel out. And then each of these dipoles contributes exactly 1/3. This is 1, and the 3 1/3 plus 1 cancel out. Okay. So, of course, something like chloroform, which has 3 chlorines and a hydrogen, well, that clearly is going to have some level of dipolar nature, right? Because now each of these is pulling electrons this way, whereas in this case, electrons are being pulled that way, right? And so if we add these together, then there's definitely going to be a net dipole here with more a negative electron with the side of the molecule, with the chlorines being significantly negative and the one of the hydrogen not being negative. So you have a dipole there. So that's an example of some of the math. Yeah, there's a dipole in that case. And so the properties depend a lot on whether a molecule has a dipole or not and how strong it is. So looking at some of the cases, a linear molecule that is symmetric, right? This would only hold for something like CO2. CO2 is the same molecule on both sides. If you had, for example, HCN, you're still going to have a dipole, right? Because the nitrogen is pulling electrons away. So that will have a dipole. But if you had something that was there's the CO2 that's linear, then it will be nonpolar. Bent polar, obviously if you add those vectors together, you see a bent molecule. You know, if you have, for example, HOH, which is bent, the oxygen is pulling electrons away for the hydrogens, and so you're going to have a dipole. It will be, change from positive on this side to negative on this side. And that's actually what makes a lot of the structure of ice, is lining up those dipoles. Trigonal planar, again, will have no net dipole if all three are the same. If they're different, of course, then you will, obviously OCH, that will have a dipole again because it's what electron withdrawing. So going from negative to positive will be like that. So it's not all trigonoplanar molecules. If you have a trigonoplanar molecule where all three of the molecules around the edge are the same, then it will have no net dipole. Tetrahedral, again, if they're all the same, will have no net dipole. Trigonal pyramidal, like methane, that will also be polar as well. So those are the main examples of whether things are polar or non-polar, dealing with the simple molecular geometries you see in the first row. We can quickly review the geometries that include 5 or 6. So for example, trigonal bipyramidal, turns out that the up and down vectors clearly cancel out, and these 3 vectors cancel out axially. So anything like PCl5, even though there's significant electron withdrawing from the chlorine, it cancels out. So it's a nonpolar molecule. Sulfur tetrafluoride is polar, right? Because it's not symmetric. You've got this imbalance of electrons, being withdrawn away. So you have so it will be more positive here and more negative out here. And then this can be polar as well. That's not symmetrical. It'll have a dipole in this direction, not up and down. If something is linear, of course, if they're all symmetric, then it won't be polar. So that'll be nonpolar. Of course, this in case it's I3 is an ion, so the polarity is sort of irrelevant because it's already charged. If we go to this case, then octahedral, it's completely symmetrical. It is nonpolar, again, as long as everything's identical. So sulfur tetrafluoride is nonpolar. Square pyramidal will be polar, and the dipole will be oriented in the same direction as its axis, because in the square plane, there's no dipole there. Everything exactly cancels each other out. And then square planar, there's nothing in the z direction, and in the x and y direction, everything cancels each other out. So it'll be nonpolar here as well. So nonpolar, polar, nonpolar. And again, of course, if the symmetry is broken here, if this were like a chlorine here, that would end up being slightly polar, because there the dipoles wouldn't cancel out. So when we talk about the dipoles canceling out, it's only if they're all the same molecule that are canceling.